couple days ago, we were talking about gravitational force. That's that mysterious force of gravity, force of attraction that acts between any two objects with mass. And we can find that force of gravity between two objects with mass by using the equation m times g if we know the value of g, right? The problem is we don't know the value of g unless we're on the surface of the Earth, where it's about 9.81. Even on the surface of the Earth, it varies a little bit. If we know the value of g, we can use this equation, however, to find the force of gravity. If we don't know the value of g, we have two options. We can go over here and find the value of the gravitational force by using gm1, m2 over r squared. Mass 1, mass 2 over r. What's r stand for? The separation distance, not the radius, although in some cases the separation distance is a radius. The Earth going around the sun, the distance between the Earth and the sun is the radius of revolution, right? But it's not the radius per se. All right, so we got the force of gravity using m times g, or the weight of an object, same thing, using m times g, if we know the value of little g. If we don't know the value of little g, we're going to go over here and find the force of gravity this way. Got it? That was a few days ago. Yesterday, we introduced this idea of gravitational fields. Gravitational fields describes for us the influence of gravity when there is nothing to be influenced. It's this area where gravity would act if there was something to be influenced. And we have two equations that we learned for gravitational field strength. One is the producer equation, gm over r squared. When we know something about what causes the field, then we're going to use the producer equation to find the field strength. And the field strength, by the way, ends up being on the surface of the Earth, 9.81 meters per second squared, or very close to that value, depending upon where you are on the surface of the Earth. And now, in addition, we've got another equation. It's F over m. This is the experiencer equation. The gravitational force, or the weight experienced by something, okay, divided by the mass of the experiencer. Be careful. This is the mass of the producer. This would be the mass of the experiencer. Now, guys, ring a bell from yesterday here? Now, you did some homework on this last night. Should be hopefully ringing a bell here for you. What I want to do is tie these together here for just a second today, and then we'll take a look at the homework that we had last night. I just got finished telling you that this equation for gravitational force, or for weight, is always valid if we know the value of little g. If we don't know the value of little g, then we're probably going to use this one for force or weight, right? If we don't know the value of little g, we can use this one to find the force, or we can find the value of little g using gm over r squared and then sub it into there. Watch what happens when I sub in the value for little g that I get from the producer equation into this one. F is equal to m times g, but g is equal to, this, by the way, would be the mass of the experiencer, right? What's experiencing the field? Okay, so we're going to say the mass of the experiencer times little g is g times the mass of the producer over r squared. What does this become? G times me times mp over r squared. So if you want to use your original equation for gravitational force, m times g, you need to know what little g is. If you don't want to use that equation, that's fine. Use Newton's law of universal gravitation. But if you don't know what the value of little g is, but yet you want to use this equation, then let's get the value of little g using the producer equation and then sub it in. And guess what happens? You end up with exactly the same thing as we did when we, or as we would have done when we used Newton's law of universal gravitation. Okay? It's not a coincidence that these equations are as they are. Okay? If we put them together, they all end up blending together perfectly so that we get the same answer using multiple methods. All right. We had 3 questions for homework last night. Starting question 1, 2, and 3 on page 218. Any questions you want to go over there? If not, then I'll pick 1 or 2, but we'll go over the ones you want to go over if you have a preference. 1B? Okay, any others? 1B or not 1B? That is the question. 1B or not 2B, I guess it would be, right? Because it's 1B, not 2B. That's the question. Yep. 2B. All right, there you go. And now we got to go over 2B. Way to wreck the joke there, Zach. 1B, and 2B. Doesn't sound as good when I say 1B and 2B. So we'll go over 1B and 2B. Those are the questions. 1B and 2B. Those are the questions. All right, number one says a satellite orbits Earth at a distance of 3 times the radius of the Earth above the Earth's surface. Using the data from this table, what's the magnitude of the gravitational acceleration of the satellite? Hey, what's another term for gravitational acceleration? What else could we call that, gravitational acceleration? Sorry? Little g, yeah, little g, or gravitational field strength. What do we know something about here? We got a satellite that's a certain distance above the Earth. We have the Earth. The producer is the Earth. The experiencer is the satellite. What do we know more about here, the producer or the experiencer? The producer, right? The Earth. We know a little bit about the satellite. Well, we know that there's a satellite there. That's about all we know about it. If we knew more about it, we could use the experiencer equation, but we don't. We know enough about the Earth, the producer, to use the producer equation. So let's go ahead and do that. G is 6.67 times 10 to the minus 11. M is the mass. Be careful. If we had the mass of the satellite here, we would not use it. We'd use the mass of the producer, if we're using this equation, that is. I'm not saying that you can never use the mass of the satellite, but if you are using it, make sure you're using the experiencer equation, okay, not the producer equation. And then R, of course, 3 times the radius of the Earth above the Earth's surface. So we're talking about the R value of R being what? 4 times the radius of the Earth? And we got to square that. Boy, we definitely want to use some brackets, I think, on this one when we're punching it into our calculator here. Let's say 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24. Let's press equals there and divide by brackets. 4 times 6.38 times 10 to the 6. And then we got to square that. I almost forgot to square that. Okay, that would be a pretty common mistake, forgetting to square that. So common that I just almost made it. We get a value of 0.611. And we could say meters per second squared, or we could say newtons per kilogram. Either one works just fine. That's a pretty low value, right? Okay, on the surface of the Earth, it's 9.81. Why is it so low in this question? Because we're so far away, right? We're 4 times the radius of the Earth away from the center of the Earth, right? 4 times 6.38 times 10 to the 6. Good? Notice, though, that it's not 0. Doesn't matter how far you go away from the Earth, it's not 0. Now, as you go higher and higher and higher, it becomes smaller and smaller and smaller to a point where it becomes negligible, but it'll never be 0. It just becomes really, really, really small. When we're in space, astronauts, NASA, they don't talk about no gravity in space. That's what we say. We say there's no gravity in space. If you ever see something that NASA publishes, they don't talk about 0 gravity. They talk about microgravity. What do they mean by microgravity? Like really, 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 really small gravity. In fact, sometimes so small that it's all pretty much 0, right? But not technically 0. All right, next question was question 2B. An 80 kilogram, oh, this is a good one to go over, actually, a really, really good one to go over, because there's something in here that can definitely lead to confusion in this. Okay, I'm glad you asked for that one. An 80 kilogram astronaut is in orbit this far, 32,000 kilometers from the Earth's center. We want to calculate, let's do both A and B, okay? Calculate the field strength at the location of the astronaut, and what would be the magnitude of the field strength if the astronaut is orbiting the moon with the same separation distance here. What's the producer here, the Earth or the astronaut? What's causing the field? The Earth, and the astronaut is experiencing it, right? So what do we know more about here? The producer, the Earth, or the astronaut, the experiencer? The producer, yeah, like we know a little bit about both, right? We know the mass of the producer and the distance away from the producer. We know the mass of the experiencer. In order to use the experiencer equation, though, we would need to know the force experienced, and we don't know that. Now, we could find the force experienced by using Newton's law of universal gravitation, gm1 m2 over r squared, and then we could use the experiencer equation. But I think it's easier just to go straight to the producer equation here. So for question A, we're going to say G is equal to gm over r squared. But be careful, the mass we use here is not the 80 kilogram astronaut. It's the mass of the Earth. And R is, what are we here? 3.2 times 10 to the 4 kilometers, or 3.2 times 10 to the 7 meters from the center of the Earth. Big number or small number here? 6.67 times 10 to the minus 11 times the mass of the Earth. Zero 0.388, 0.389. Newtons per kilogram, or we could say meters per second squared. So it's small again, right? Not quite as small as it was in the first one, but the distance isn't quite as big either. Question B, what would be the magnitude of the gravitational field if the astronaut was orbiting the moon with the same separation distance? So what changes here? Not the astronaut, not the experiencer, but the producer, right? We're changing from the Earth to the moon. So we're going to say for question B, same equation, G is equal to gm over r squared, but different mass. But be careful here. The temptation, because we know intuitively we're going to use a different mass, right, since we're going from the Earth to the moon, the temptation is to use a mass of 80, because that's the other mass that's given to us, right? If we think about that deep down and we understand it, then we know we're not going to use that because, well, we got to use the mass of the producer, just like we did here, and the producer is the moon this time. But sometimes we get careless, and because we have another mass that we haven't used yet, we sub it in, right? There is, I believe it's still there. Every year we switch around your test a little bit, but in the past, I've had a question on the test where you've been given two masses, the mass of the producer and the mass of the experiencer, and you've been asked to find the gravitational field strength. Now, I'm not going to tell you which mass you're going to use in that particular question, the producer or the experiencer, but I will tell you that if you're finding field strength, you're not going to use both masses, right? Okay, what a lot of people do, what I'd say almost half of people do, not quite half, but lots of people will do in that question is to say, oh, look, I got two masses given to me. I'm going to use F is equal to gm1 m2 over r squared. Well, that's fine if you're looking for force, but just because you're given a mass doesn't mean you're going to use the mass. Got it? We're given the mass of the astronaut here. We're not going to use it, okay, unless we're looking for force. All right, the mass of the moon is 7.35 times 10 to the 22, yeah. 7.35 times 10 to the 22, and the r is going to be the same value, 3.2 times 10 to the 7, and we got to square that. We're going to get a bigger value or a smaller value here? Smaller value, and how come? Like quite a bit smaller, actually, right? How come? The moon's smaller. The moon doesn't deform or dent the fabric of space-time as much as the Earth does, so therefore the field strength would be weaker. We end up getting 4.79 times 10 to the minus 3. And again, we'll say newtons per kilogram, or we could say meters per second squared. Is that okay? You guys comfortable with that? Good. Last topic of the unit. Get us ready for our unit test on Tuesday. We're talking about satellites today. Generally, we define a satellite as something that orbits around something else. Give me an example of a satellite. Sorry? The Hubble telescope. Okay, the Hubble telescope orbits around something else, orbits around the Earth. The International Space Station orbits around the Earth. Good. Yep. The moon orbits around the Earth. Good. So everybody so far has talked about things that orbit around the Earth, but we've had two what we call artificial satellites, and then one thing that we call a natural satellite. They're all satellites. It's just how they get there. Okay, the moon is naturally there. The International Space Station and the Hubble telescope are artificial because we put them there. Okay, they're all satellites, though. Give me another example. Yep. The Earth is a satellite of the sun. The Earth orbits around the sun. What do all four of those things have in common? The first three had in common that they orbited around the Earth. The last one is the Earth and orbits around the sun. What do all four of them have in common? They're in space, okay? Well, they orbit in the elliptical path, sure, but it's pretty close to a circle. We're, in fact, so close to a circle that we're going to call the force that keeps them in orbit around the central body a centripetal force, even though it's not necessarily exactly a centripetal force. What causes that centripetal force in all four cases? Gravity. Gravity causes that centripetal force. So we're going to say, in general, a satellite is anything that orbits around something else or anything that revolves around something else. But we're going to specifically talk about the satellites that orbit around something else due to gravity. We're going to look at natural satellites and artificial satellites. In the end, the analysis is no different, whether you've got a natural or an artificial satellite. In the end, they're going in more or less circles. Therefore, we'll say that whether it's a natural or an artificial satellite, there's a centripetal force. And we'll say that that centripetal force is provided by gravity. So the centripetal force will be equal to the gravitational force. Now, as we said, satellites, they orbit around something in more or less a circular path. They experience the centripetal force because of that, and generally are held in orbit by gravity. These are the ones that we're going to focus on. These satellites that are orbiting around something, experiencing a centripetal force, which is caused by gravity. Which makes the analysis actually pretty easy. Here's what we're going to do to analyze these satellites. Since the centripetal force is caused by a gravitational force, we're going to set those two equal to each other, just like we did earlier in the unit when centripetal force was caused by friction. The centripetal force is mv squared over r, and the gravitational force is g m1 m2 over r squared. Well, we can simplify this a little bit because there's variables that appear on both sides. R appears on both sides, so we can actually cross off one of them, cancel out one of them. So now we're left with m times v squared equals g m1 m2 over r. Make sense what I just did? What else can we cancel? One of the m's. Now, let's pay close attention here. This is, whoops. Let's make this one the mass of the producer, this one the mass of the experiencer, M1 and M2, the mass of the producer and experiencer. What mass is this going to be over here? It's going to be the experiencer. When we have something orbiting around, we calculate the centripetal force, we use the mass of the thing that's orbiting around, which would be the satellite. We could call it ms, the mass of the satellite. This would be ms, the mass of the satellite, right? What are we left with? mp. So the equation becomes v squared equals g times the mass of the producer over r. This equation isn't on your data sheet, but that's okay because you can figure it out by setting FC equal to FM. It is the equation that describes satellite motion. The speed of the satellite squared is equal to GMP over R. Now, the reason I haven't square rooted that is because since it's an equation that we derive and doesn't appear on our data sheet, I'm just leaving it in a more general form because we may have to solve for that variable or some other variable, right? Just rearrange it to solve for whatever variable you need. Let's take a look at an example. And then we're done the unit. The moon, Earth's moon is 3.844 times 10 to the 5 kilometers from the Earth. That looks like it's from the center of the Earth. Now, if it was from the surface of the Earth, what would we have to do? Nope. If it was from the surface of the Earth, we'd have to add the radius of the Earth there, right? Because we always need the distance from the center. To determine the orbital speed of the moon, well, the moon is a satellite of the Earth, so we're going to say FC is equal to FG. We're going to say mv squared over r equals gm1 m2 over r squared. R's cancel, m's cancel, and I'm left with v squared is equal to g times the mass of the producer over r. We're looking for the orbital speed of the moon. How fast is the moon moving? Do you think it's going to be fast or slow? I think it's going to be pretty fast, yeah. V is going to be the square root of 6.67 times 10 to the minus 11 times the mass of the producer, which would be the Earth in this case, divided by R, which is, that's 3.844. Make sure you make that in meters, times 10 to the 8 meters. We don't have to square it this time because one of the R's canceled out. Let's figure this out now. 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24 divided by, let's go 3.84 times 10 to the 8. It's in meters, remember. And then we got to square root that. 1,018. Which we're going to round to 3 digits because of the 6.67 and the 5.97. 1.02 times 10 to the 3 meters per second. So the moon is orbiting around Earth at 1,000 meters per second, 3,000 kilometers per hour. That's pretty quick, eh? 3,000 kilometers per hour. Oh, perfect timing. Hey, we got a unit test on Tuesday, but before that, we have 2 questions that we have to do for homework for Monday on page 278.